Hello and welcome to part 8 of Dev Maths and Stats Refresher Course, Lecture 6. So now we're looking at the bit of maths here, which is percentages, compound interest and so on, which you need to be complete experts at. So on the worksheet compounds, we've got a classic situation where an initial quantity is growing over time and you have a given rate of interest. So you should be able to do this using pen, paper, calculator as well as a spreadsheet. So what would the value be after one time period? So here we've got growth, initial thing is 500, growth rate of 3%, so after one time period we would have 500 increasing by 3%. I think that's the most efficient way to calculate it, like this, so you can work out that would be so 1% would be 515, we'd hope. Let's see if we get anywhere like that. So the time periods here, this is going to be time period 1, 2, 3, 4. So, oh, that's not very good. You can just cut this down like that, and Excel guesses you want to increase this. Yeah, so it's gone to 515. So great, that's after 1 year, it's gone up to 515. You can see the formula here. Okay, can you predict the value reached after 15 periods before using the spreadsheet to check? So if you're trying to do this for 15 periods, it'd be 500 times, and then times 1.03 times 1.03 again to the second, third, fourth, so it would just be like this. So 500 times 1.03 to the power 15 will give you the predicted answer. So let's 500 1.03 to the power 15. So that's the prediction. So let's see how it goes after that many time periods. So we come down to here, we want to get 778. So the prediction works out okay. Good, so this is growing over time now. And oops, that's the question. Classic question is, predict the number of periods needed to get to 1000. So 500 times 1.03 to the power n, after how many years do we get to 1000? Well, what is n? Well, first step might be this, is equal to 500, no, 2, because 1000 divided by 500 is 2, and then you might take logs of both sides, so log of 1.03 to the power n is equal to log of 2. You could use base 10, any log will do. Then you can use the rule that says you can bring this down to here. So n is log 2 over log 1.03. So n you can read log up equals time for formula. That doesn't look very promising. Okay, let's turn it upside down. Otherwise we're going to get there to £1,000 within half a year. Should be a good rate of return. Okay, so 23 years, so between the 23rd and the 24th year, should hit £1,000. 23rd and 24th year, so that seems like, oops. So again, that's correct. So you should be able to do that on Excel. You should be able to do it by hand with a calculator, understand the principle of that. Okay, now we go to the final thing, which is CBA, or cost benefit analysis. So column C and D gives costs and benefits over time for projects starting in year 0, and I think it's got the typical pattern, which is that it could be something like building a clinic, building a road that needs some maintenance, so that a massive cost up front and then a steady cost of maintenance in future. Supplies. Here, the benefits start to build up, and then the benefits in future exceed the costs. But up front, you've got relatively few benefits and massive costs. So the question is this future stream of costs, is this future stream of benefits worth the costs that are up front and then the ongoing costs later on? And the discount rate is crucial in this, as you'll discuss at length. We're analysing these things this year. So concrete examples are something like a big infrastructure project, like a road or something, or electricity plant or something like this, or it might be a hospital. So after how many years do the benefits of the project outweigh the costs? Okay, so the naive answer is totals. Do a total like this. It's like that. You want to fix that. Fix the 6 bits. There you go. That's hanging up. It's not adding up. $2. Yeah, so that's adding it up. So this is adding it up. So it looks on this naive estimate that in cash terms, the benefits get bigger than the costs after 19. In terms of total cash outlay, after 19, 20 years, the benefits outweighing the costs. However, this is not the way it's normally done, because for reasons I should not go into the philosophy now, but for a number of reasons which you'll discuss extensively, pounds spent, dollars spent and received in the future are valued now much less than their face value, and the further they are in the future, the less they are valued, for various reasons, like the uncertainty of ever getting to 25 years means it's worth less now. Plus, if you had $2,000, $4,000, $5,000 now, you could invest it, so but in 25 years' time, it'd be worth a lot more, and so on. So we don't value that in the same way. We discount it. So, in fact, these, you actually write it more like this, which is so this is gross crash. You have a column which showing the discounted. So costs. So this is the value today. So this one that's 25 years in the future, this cost here would be equal to this, reduced by fix that. So this expression here means 5 divided by 100, so that's your 0.05. So this is 1.05, so it's 1.05 to the power of 25. So you're reducing it by 5% for the 25 years to bring it back to the value we see. So in current days terms, £5,000, $5,000 or whatever, 25 years in the future, is only worth this much. Oops, I made a small mistake there. I need to fix this on column B. Otherwise, so when I pull this across to here, it's going to do the same calculation, fixing that here. working the net present value there. Pull this back to here. So these are the values in present day terms, and now we can add these up. So we'll put the totals. So these are the net present. Actually, I'll stick this here. So the net present value is the benefit minus the cost. So that shows effectively the profit in each year, the benefit minus cost, discounted back to what we value at in this current time when it's starting, and then we can total these up. So this is total. Oops. So the total net present value is the total. So I'm going to start from here. So I'm going to fix that row. So add that up. From there all the way to the same place. It's resisting the dollars there. The reason you do that is that as you copy it down, it stays as that gives you the total. So you're making loss, making loss, making loss, making loss. So actually, gosh, it seems we're making loss all the way down because the future discount stream is valued so highly. So it seems it's going to take a number of years for this to break even. Let's keep going. Gosh. Years gone haywire. Copy this correctly, hopefully. Still not broken even. Gosh, so it's going to take 46 years. Yeah. So it's much longer once you take account of the future discounting, because the benefits are generally lying in the future. So being the advantages are in the future, the disadvantages are in the present. And when you discount the future at 5%, which is quite a heavy rate, that means that after a few years' time, that the value has shrunk quite considerably in terms of present day value. So the fact that you've got a cash profit for so many years in the future, it's all discounted, so it's a long time to chip away at this initial huge disadvantage. So it wouldn't break even in net present value terms until 46 years in the future. To look at the next part, the internal rate of return, we could do it just changing the way these totals are being calculated a little bit. So we can have the total showing at the top. So I'll put here the total. And this is going to be from here down to so it's just adding up the rows, basically down to row 1000. So that total of 5767. is the same as this one, because that's the number of rows you add. So as we add more rows, you can see that this net present value is increasing, because in the future the benefits are outweighing the costs. So even with the discounting, it's increasing the net present value. But if we copy this down, so here it's been going for 132 years. Notice that it's so far in the future that these cash costs and benefits are now worth just a few dollars in today's money. So the overall total value of the project in today's terms is only increasing very slightly. And if you wanted to be pure about it, you could then keep dragging this until the point it gets to, I think it's a few hundred years, just to see the limits. Somewhere down here. No, that's annoying. I need to put these years in properly because the years are not updating. So 276 years in the future, it's down to virtually less than a penny being added onto the project value now, so it's stabilised. So it reaches a limit of $15,333. So that's the final net present value at a rate of 5% interest rate. Now, one interest rate that's of particular interest, because it's hard to just pluck interest rates out of the air. There's so many factors and considerations that go into setting an appropriate one. So one thing that project people like to think about is what rate of interest would mean that we exactly break even. In other words, this limit of the project value over the long time horizon is equal to 0. Which is why I put it up here, so we can just do it by trial and error. So you obviously have to decrease a bit. So if it was down at 2%, that would greatly increase it. But what would actually make it equal to 0? It would have to be bigger. 7% would be making a loss. 6%, that's close as it could be. 5 and a bit percent, perhaps. Yeah. So you can do it by trial and error, or you can use something which is on the data tab here, which I've already brought up actually. Under waterfall analysis. This is very useful. You basically click on the thing that you're trying to set, and using something called goal seek, you can say, okay, I want this cell to be equal to whatever value, so we'll have a 0, and I want to change this cell to the necessary value. And Excel tries to find what this must be to make this equal to your target, I said 0, and it's going to find 5.6%. Okay, so the internal rate of return here would be 5.6%. So in other words, if interest rates went above that, it wouldn't be worth doing. Below that, it's worth doing. Okay, I think we set this back to 5%, I think, to answer the final question. Okay, let's say the government wants to increase, the private contractors want to increase that 100,000. What's the maximum value the government should accept? Well, the government should extend anything up to the value that makes the net benefit 0, under certain assumptions. Whether the commercial value really represents the best decision making process for the government or not. But if these costs were to go up so high that this became 0, so what should this go up to? Well, again, you can use goal seek to say, what if, to make this equal to 0, to make the overall net present value of the product goes down to 0 because these private contractors are charging too much, how much would they have to charge? Hopefully it's going to be able to come up with a value for that. It doesn't like it. Oh, okay. Oh, looking at the wrong one. There we go. Okay, so 115,000. So at that, this 5% interest rate, if they charge another 15,000 for that initial outlay, then that would mean that anything more than that would be no longer worth doing the project. Okay, so that's the idea of net present value, which I say is a really important one, and the thinking behind what determines interest rates is sometimes very controversial and always important. Okay, so that's the end of this percentages section, so thanks for watching.